G'day. My name is Benjamin Carlisle. I'm a software engineer, I'm a systems engineer, and today I'm going to be talking to you about a tool I've been developing in my free time for systems engineering purposes. It's a systems engineering tool that is designed for educational purposes primarily, but I hope will also be useful for actual engineering. At the moment, there's no real launcher, so we're going to start it with java-jar on the systemdesign.jar file. I'm using the Debian package installer, which puts the file into user share Java. If you choose the zip file instead, then you just need to unpack it anywhere and run java-jar on that same jar file that you've unpacked. It requires Java 8 and it requires JavaFX, so that's the OpenJFX package on Ubuntu or Linux. Here we go. This is the tool. It's very simple. It's very sparse at the moment, well, until you add an item. So what we're going to do is we're going to start to add something to our model. We're going to add physical things first. You see that there's a rectangular shape here. Rectangular shapes usually mean something physical, something that exists, something that will be built or designed. So let's think of something to build. How about, well, I don't know, a tea making system. So say we have a tea making system. We want to ultimately have some sort of user for the system. So we're going to have, say, a tea drinker, and they're going to do something, okay? So we're just going to save this to put it somewhere, because as you start to move between levels, it needs to exist somewhere. It's not just one set of files or one file, it's a directory hierarchy, which is the structure of the model. So let's start. We'll go temp tea making service. That is excellent. So what we'll do is we'll say the tea drinker is going to do something. It's going to have a function, and that function is called drink tea. Oh, okay. Well, we've got something up here now. We've got an unallocated functions list. So we've got functions that have appeared, and instead of being square or rectangular, we have an ellipsis, and that it tends to imply something that's more logical, something that's more ethereal nature. It's not what something is, but it is what something does. So a tea drinker drinks tea. Now, often with very simple models, there'll be a lot of synergy between these two views, a lot of overlap. As you get to more complicated models, it actually helps a lot to have these views separate. But what you'll see, in fact, is that form follows function, and for very simple things, the definition of a certain item will actually often be the thing that does the function that it does. So a tea drinker drinks tea because they called a tea drinker because they drink tea. So, very simple. Good. Now let's switch back to this physical view and we'll say, well, the tea making system's got to make the tea, so we'll add a function for that as well. We will make tea. A function is typically a noun and a verb. Well, a verb and then a noun. So you're going to do something on something or with something. So you're going to do something, you're going to have some descriptive transformation of some input to some output. So let's add one of those. So we'll take the making tea and we're going to actually add a flow. I'm holding down Control to drag these things out. You can see a little link icon pops up. So what you get is a flow. And we are talking really fundamental systems theory here. We're not talking about a specific engineering standard here. If you look up Wikipedia and look at open and closed systems, you'll see flows. Flows of information, flows of materials, and flows of energy. Those are the kinds of things that you typically flow from a function to another function, and then ultimately to the systems that encapsulate and implement those functions. This flow has a type which is called tea. We are making tea in a tea making system, and that tea is being transferred to the tea drinker, possibly by some sort of orifice such as a mouth. So we have our system. We have, at this very top level, we have a description of our problem, more or less. but it doesn't tell us anything about how we're going to solve the problem. And this level really shouldn't. This level is our starting point. It describes the problem, does not describe how we're going to solve the problem. That's for the next level down. So let's drill into this tea-making system. We're going to navigate down into this system. We can also do this by double-clicking, and we'll navigate down and we see another blank page. But no longer completely blank, because we've got a little warning up here which says, you know, this tea making system, it has an interface to a tea drinker, and so its subsystems should as well. If you're making a tea making system, if you're designing a tea making system, then the things that you design will have some interaction with the tea drinker. So let's flow it down. We usually have a flow up or a flow down. Flow down means take what was given to you from above and accept it. Flow up means reject what was given to you from above and undo whatever is causing the system to think you should have that. So, but in this case, we'll just flow down. Flow down, the tea drinker exists. If we switch over to the make tea function, our tea making system has a make tea function, which we haven't yet designed. We go to the make tea function and we find the tea drinker is also here as their drink tea function. So how do we make tea? Well, we'll need certain parts. We'll need some sort of concepts. We'll need maybe a kettle would be helpful in making tea. So we're going to rename this to kettle. We're going to add a teacup. We might even add a, what do you call it, a tea pot. Just for completeness, maybe we should also add a tea bag. And we might also think that we might need some water in the system. So we'll make some water source. We might not actually care too much about what that water source is, and we might also take some sort of power source, such as an electricity supply. So we're starting to get these elements together. We don't want to navigate just yet. I might just give this a save. File, save. You can also go Control S, open, new, all the normal things are there. There's an infinite undo buffer, so anything you don't intend to do, you can just undo, and anything you didn't intend to undo, you can always just redo. The help menu does nothing at this point. There is no about. These two things are useful. We see the physical view getting filled out here. We know that a tea drinker exists alongside the tea making system, and we can see all these items that are in our diagram. And at the logical side, we can see we're starting to see these external things as well. The functions of these items will appear over here as we allocate them to the make tea function. So we're going to have a teacup. We know a teacup contains tea, or contain tea, in fact, is its function name. So we'll take it over here, contain tea, done. Okay, so the teapot, well, it's probably going to have a function of brew tea. That's a reasonable verb, noun. It's going to brew tea. It's going to use a tea bag to do that, which might have a function, say, of infuse tea. Or infuse water, in fact. It sort of infuses tea into the water, doesn't it? So that's a practical thing we could think about. A kettle might heat water. And a water source might supply water. And a power source might do a similar thing, but for power. Okay, so we're getting our sense of our functions. Now, we've got a new warning down here. We've got a couple of warnings. One says, nothing we're doing here yet supplies tea to the tea drinker, and that would seem to be a problem, so we need to fix that. It also says check function allocation. Well, that's just a little indicator to look over here and see you've got an unallocated section here. Well, we're going to make sure that the system understands, the tool understands, that those are all things that should contribute towards making tea. They are part of the make tea design. So we're going to put them all up here, and they will all appear right here. So here we are. Here is our design on the logical side. We know what it's going to do. We know we have all these items that are going to do different things, and these are the things that they will do. So we're going to heat water with a kettle. Well, we're going to need some power from the power source. We're going to need a water source to supply us some sort of water. We know that it's probably tepid water. It's not hot water yet, so that's why we have a kettle. So we have a power supply that is going to supply us probably, let's just be clear, we're just probably going to provide electricity. And these are design decisions we're making. We could make other design decisions. We could have a water supply that supplies water already hot. We could have a teapot that could have a kettle that brews the tea within the kettle itself rather than needing a separate teapot. So whenever we create these items, we're actually making design decisions about the solutions. And there are alternatives, and we can consider what those alternatives are as we go through the process or later on as we look at what are known as trade study, where we trade off the possible designs and their benefits. We consider a baseline design and consider the alternatives that could exist. Well, the infused water is going to interact with the brew tea function, and it's going to supply, let's say, just tea infusion. It's not tea itself, but it's the chemicals that exist in those leaves, and away you go. So the heat water function is going to supply hot water. Okay, and contained tea is just going to take probably the real tea, if we get that spelled correctly. Okay, so the last one's interesting because this is external. The system already knows there should be a flow of tea to that function. So when we drag this one out with control drag and we link it and let go, well, it already knows. It knows it's tea. And it also knows that that is no longer a problem. We are providing everything we said we would provide in the next baseline up, called the functional baseline, is actually supplied in this baseline, the current baseline, which is called the allocated baseline. So we meet everything we should do. Now, we might have specific requirements we need to deal with at a more detailed level in a more detailed way, but this is our system. This is our system design, and you can see that the interfaces have all drawn themselves as well. As we've drawn these flows, the interfaces have been drawn on the items as we've gone through. So then we have to think, well, what do we want to design next? Because we can actually design to an arbitrary depth. Let's go to the kettle. Now we see that there are more functions, more items that it has to interact with. So we might as well flow down all of these and give ourselves the context we should have. Flow down, flow down, flow down. Look, we've got a water source, we've got a power source, and we've got a teapot. That is the context of this design. And the heat water, we've got something supplying water, we've got something supplying power, and we've got something that we're going to brew tea. So we can understand what this thing is for. We know what it's for, and the more we know about what it's for, the more accurately we can design for the intended use. So let's design it. We might have a water containment unit. We might have an element, a heating element. We might have a transformer, like a power supply within the kettle. And we might actually start to understand type a little bit more here, and once we've got down to this level, we might say that we don't just have electricity happening here. We have coming in from the power supply. We might actually say that's mains electricity. We might have a different classification for electricity within the kettle system. So we're actually building the kettle here. We can see 1.1 kettle. It's part of the system that we're contained within, and we're going to supply various things. Let's draw the functions so we don't have to draw these interfaces and sort of guess. So the water containment function unit's function is just to contain water while it's being heated. The power supply is going to transform power. and it might in fact be to transform out electricity. The heating element is actually to heat the water. Whoops, try again. Heat the water. And as you go over just even a few levels of this kind of design process, you can actually build up a very large system and to a lot of detail. So we've again got a check function allocation warning, which says we haven't told it what these things are for. So we're going to contain water is under the heat water function. The heat water is under the heat water function, but the heat water is different here. It's at a different level, so it's a slightly different function. And we're going to take the transform power. You can ignore these external ones. In fact, they'll be gone in the next revision. So we know that the water containment is going to provide hot water eventually to the brew tea, and there it goes, and there our warning goes. We're going to supply water into the containment unit as well. Another warning disappears, and we get that flow that we know exists. So the supply power is going to actually go into the transform power, and that's providing electricity. But we're going to probably change that to, let's see if this works. We're going to change that to mains electricity. Ooh, that was brave. Let's see. We're going to actually flow that up. And we're going to flow the other electricity flow up as well. So let's see if that works. We save it, we go up, and look at that. We now have mains electricity. So we're able to, as we've refined the design, we can actually look back up again here, and we can refine this original design up here while we're refining the lower levels. So that's how this, what this multi-level approach does for you. It's matching up the functional baseline and the allocated baseline, and you can start to modify either one as you realize that there's an error or a problem. So let's go to the heat water. We're nearly finished. We're going to transform power. That's going to be some sort of internal power, say DC electricity. Perhaps, I'm not a kettle engineer, I do not know what they're using internally, whether they still use AC or DC. But we're going to provide, that function is going to provide heat to the contained water. And you can see how this works. You can see tepid water plus heat equals hot water. Of course it does. It's easy. Mains electricity becomes DC electricity after transformation. These things make sense. We can understand them. Even somebody who doesn't really understand all the technical engineering detail can understand what this design is, how it hangs together, why these things exist. And that's the kind of nature of this design. And again, we can go up, we can go up, we can see all these levels, we can see how things are getting implemented, we can see why these items exist and what their functions are, why a function exists. We can see how this whole thing hangs together. And that's what systems engineering is mostly about. We are looking at getting a system that is large. It's going to take a lot of individuals, a lot of teams, in fact, to build a large system. And we take that whole system and we bring that knowledge together in a uniform form, sometimes called requirements or various other things. And we take that information and bring it into one form, one model, and we let everybody know what they need to build in order to get the whole system to work as it should. These kind of very broad systems engineering techniques, which are very high theoretical in some sense, are not going to be the most appropriate way to do a detailed software design. They're not going to be the most appropriate way to do a detailed mechanical drawing. But they are an effective way to bring together the engineering expertise of different disciplines into a cohesive engineering organization. And that is the kind of thing that we systems engineers are all about. But another thing that we like to think of ourselves as is some sort of guardians or custodians of core engineering knowledge. And we're not talking about materials knowledge, we're not talking about Fourier analysis, we're not talking about mathematical skills here. We're just talking about how engineers should approach problems and how engineers can effectively work together to solve big problems across a large organization. And the kind of disciplines that we talk about with configuration management and requirements management and managing design, these are the kinds of disciplines that actually apply in every engineering discipline. And to some extent, systems engineers sit in the middle of that activity across different disciplines, and we keep those disciplines connected to each other in a way that allows them to speak the same language, and we speak that a common language which they should understand, and we should understand that common language when they speak it to us. That is systems engineering. That is this tool. And this is me signing off. Thank you for listening. I hope you give it a try.